Welcome in. All right, so fluid statics, density and pressure. This is made for grade 11 physics students. However, of course, you can take a look at this. So it has about 8 questions. Now I may divide the video into 2 portions, kind of cover first half and then second half. And so you might see that happening. Now, if you want to get a hold, of this particular test, which has been set up for students, I'm going to put it as usual in the description, so you can download it. It's going to be free, and then you can work on it, come back to the video, and try to see if you can tackle these particular questions that you have. All right, so just a little bit of item, in terms of cleaning things up. So please do note that I will, at least for this particular set of questions, I'm going to be rounding final answers to 3 significant figures. If you've forgotten about sig figs, I'll put up a link up above there for you in case you want to refresh yourselves. And I will provide answers in SI, the metric standard units, unless the question asks me otherwise. And I'll do no really rounding in the intermediate steps. All right. Okay, so let's get started. So here's question number 1 that we have. So for this question, it gives us 3 parts. So this is part number A at first. So for part A, it says a spherical object, with a radius of 15 centimeters has a mass of 3.2 kilograms. What is the object's density? So it's just kind of a steady, easier question to be able to answer. So let's write down what is given. So now the object is spherical. So you kind of have to remember what the volume is of a sphere. So this is 4 over 3 pi r cubed. For most part, if you have it on your formula sheet, you can certainly use it. If you start using this long enough, you probably will remember. So that is the first item. Now the radius itself that we have in here is 15 centimeters. Now because we kind of want SI units, I'm going to change this back to 0.5 meters. So that's just because of a prefix. And then I have my mass, which is equal to 3.2 kilograms. And so for that, that's already in standard, metric units. Now, if you recall, so if you're going to be working with density of any kind, so the equation for density is simply mass over volume, right? So this is the standard equation for density. And if you're going to be using this, well, we have our mass, we certainly have our volume, although I guess we kind of have to substitute the radius back in there. So I'm going to do that all in one step. So my density is going to be equal to, so 3.2, everything is in metric standard units, so I can kind of drop them, and then divided by, so this is going to be 4 over 3 pi, and then my radius, and my radius is going to get cubed in here. So if I substitute this in here, all right, so that's my volume equals, so there we have it. So this is going to have, so 226, and since I'm rounding to 3 significant figures, I'll leave it at that, and that's going to be kilograms all over meters cubed, and that would have been your density. So that's part A right there for us. All right, so now part B. So if the density of a substance is 13.6 grams per centimeters cubed and its mass is 2.5 kilograms, then what volume does it occupy? All right. Okay, so now let's try to see. Now they do give us the density. So this is in terms of the given pieces of information. So my density in this case is given. I kind of know what this substance is. But anyway, so I'm going to just write it in. So 13.6 grams, and this is per centimeters cubed. Now, for those who are familiar with density, so if it is given per grams per centimeter cubed, this is equivalent. So actually in SI units, because we need kilograms per meter cubed. So this is the same thing as 13.6, now times 10 to the 3, and it changes to kilograms per meter cubed. So that always is the equivalence. Now you can do the unit conversions to convince yourself if you want to. So I kind of remember that conversion. It's very easy to go between grams, kilograms, and then centimeters cubed to meters cubed. So we can certainly do that. All right, so with this, now that we have our density, and we are told that the mass is 2.5 kilograms. This is 2.5 kilograms. We can certainly find out what the actual volume is. So again, we're going to use exactly the same formula, which is this one right there. So if we're going to use that and substitute it back in there, we can solve for volume. So let me do that. So this is 13.6 times 10 to the 3 equals 2. This is 2.5 and all over V. So now if you isolate for V, you're going to get V equals, becomes on the other side, and you're going to do 2.5 divided by 13.6 times 10 to the 3. And let's see what that will give us. So 2.5 divided by, and so within here, so 13.6 times 10 to the 3. And that's going to give us a very tiny number. Okay, so I'm going to put it in scientific notation. So it's going to be 1.8 and I guess 4 to 3 significant figures. And we have 1, 2, 3. This is going to be times 10 to the negative 4 meters cubed. All right, so there you have it. So that's the answer for this one. I don't think they asked us to put anything else in there. That is it. All right, now let's take a look at C. So I'm going to add an extra page in here so that we can take a look at that one. What would be water's mass under the same volume as in the previous part? Okay, so what would be the mass, okay, under the same volume? All right, so this one we have to think back. Okay, so we want water. Now, the tricky part is, I mean, you should know what the density of water is once you start studying fluid statics, okay, and pressure and density. But for those who don't remember, so this is the easiest one to remember. Okay, so water, the density itself is 1 times 10 to the 3 kilograms per meter cubed. Sometimes you can actually put it to more significant figures if you like. And this is at a particular temperature. I believe it was at 4 degrees Celsius. But typically you're going to use this regardless of what exactly the temperature might be in here. Okay, so this is commonly used for water. So really it's 1,000 kilograms for every meter cubed, okay, is the density. Now the volume that we had from the previous example, okay, good, I left it on the calculator, so I'm going to just use that. But the volume is 1.8, 38. Okay, so here it's good to actually use the full thing. If you're going to use 1.84, that's fine. Okay, so unless your teachers tell you otherwise, you have to kind of be careful. But I said I'm not going to round in intermediate steps. Okay, so I'll just try to be consistent with that. Okay, so in this case, again, so because density is equal to mass times volume, which just simply means, okay, that mass is going to be equal to your density times volume. Now this is very relevant for us in this particular chapter, so that you know that mass is always density times volume. Well, since we know these two, okay, so these are two that are provided to us. So here's the density, here's the volume that we have. So I can take them. Now this is already on my calculator, which is super convenient, and then times 1,000. That's the density itself. So there you have it, okay? So that mass would have been equal to 0.184, okay? So again, to 3 significant figures, and that's going to be kilograms. So it's really not that much, right? So it's about 184 grams, okay? So it's not that big at all under these particular circumstances. All right, okay, so there you have it. Okay, so notice that so within here, so I just want to point out from the previous one, the mass of this was 2.5 kilograms, and yet water was only 0.184 kilograms. And that is because water, as you can see here, so the density, now by the way, this was actually mercury, so, or at least it should be mercury. That's what mercury's densities is. It is about 14 times as dense as this. Okay, so it's going to have much more density, okay, within there. So the same amount of volume is going to be so much heavier. Okay, so that's what you have in here. So that's the first example that we have run into. Here is example number 2. Okay, so let's try to see this. This has 2 parts in here for us. So let's take a look. So again, so part A first. A normal force of 450 pounds okay, is spread over a circular area of radius 35 centimeters. What pressure is present? Okay, so this isn't very difficult. So here, let me just try to draw this out for you here. So if you have, let's imagine this is kind of a circular item, and what it's saying, so now it's the normal force. So normal just simply means it's perpendicular to the surface. And of course, so for pressure, so pressure is equal to the force over the area, but it is indeed the normal force that we're looking for, right? So we don't want it at an angle. If it is at an angle, we need the actual perpendicular component, okay, in there. So within here, so this is 450 pounds, okay, that we have. We can certainly change this to newtons because they give us what the actual unit conversion is there. So 450 pounds multiplied by, and now this is going to be 0.225 pounds, and this is 1 Newton. So what would that be? Okay, so let's take a look. 450 divided by 0.225. Okay, so that's pretty good. So this is 2,000 newtons. Okay, so that's a nice number right there. And now we want to know what the pressure is, okay, with the radius of this circle. So this radius right there, well, it's not a very nice arrow there. Okay, so that this radius r, and that's 35 centimeters. Now, we want to know what the surface area is. So again, so this is pi r squared. So that's the area of a circle. So this is going to be pi, and we need this in metric standard units. So that's what we would have there. We have to square that. Okay, so therefore, from here, the pressure is equal to, so 2,000 newtons. Okay, so that's what that is. And then this is going to be pi multiplied by 0.35 squared. And we'll get our answer. All right, so let's try this. So 2,000 answer divided by, and so now again, so pi multiplied by 0.35 squared. And what do we get? So we get 5,001. So I'm going to try to round this off. So 196.8. This is going to be in pascals. That's the SI standard. If you have newtons over meters squared, so that's pascals. And to 3 significant figures. So it's going to be 5, I guess 200. So you have to be careful how we write this. Okay, because of this moves over. So you can certainly write it 5.2. Okay, 0, and this will be 3 sig figs, pascals. All right, so there you have it. So that's for part number A. Now, part number B, if a pressure of only 370 pascals is needed to puncture through a surface, all right, then what force would be needed if the surface area is 1.8 millimeters cubed? Ooh, okay. So let's write all of these things down. So what is given? I'm trying to puncture through a surface. So 370, so that's the pressure. That's pascals. Now the surface area, this looks very tiny, which is 1.8 millimeters cubed. All right, so now be careful because we're going to need this in meters cubed. So in here, now you may or may not remember, okay, so this is just prefixes. Now millimeter, there's 1,000 millimeters in a meter. Now if you're thinking about prefixes, so coming from, milli, so going from milli to centi to deci, okay, so it's basically 3 over. However, right, because you're cubing, it's going to be 3 times. So I'm going to just do this with regards to just kind of remembering. So for us, 1 meter, okay, so that's 1,000 millimeters, and we have to cube this. Okay, so I'm going to just write that out. You can use prefixes if you like, and that's going to give us the answer. So now you can put it in the calculator. Okay, so 1.8 multiplied by, so 1 divided by 1,000, and this is going to be all cubed, and it's very nice. It gave it to us in scientific notation, and I was going to write that anyways, but hopefully, okay, you can see that in here. So that's meters cubed, okay, from the calculator. So now we have the pressure, we have the area itself, so we can find out what the force is. Okay, so from the equation, or the definition of pressure, which is just force over area, so we have this and we have this. So that means that force is just simply pressure times area, and we can substitute these two in there. Okay, so let's do that. So I have this already, and now this multiplied by 370, and notice how tiny this is. So this is 6.66 times 10 to the negative 7 newtons. That's a tiny force, okay, to puncture through this. So if it was only 370 pascals that you needed, I mean, you can blow on this, okay? So negative 10 to the negative 7 is a puny force, okay? And so that's what this example would give us. So that's problem number 2, okay? That one's done. Here is problem number 3. So it says a large dam is built to withstand the pressure of the water. So if a dam is 45 meters deep and 50 meters across. All right, so let's try to visualize this. So I guess you have some kind of a dam. So it's kind of like this, right? So you're going to have some dam built out. I'm going to try, okay, so that you can kind of visualize this throughout. Now, the dams typically on the bottom are going to be much thicker than they are at the top, and that's because the pressure itself, right? So the pressure coming in from the water. So if this is kind of how the water pressure is going to be coming in, so it's always kind of perpendicular to the surface. So as you have, so this is the pressure which is exerted. And now we know that, the pressure, the deeper you go in a fluid, okay, the higher the pressure is, because there's just more volume on top. So it is asking us here, so this is what we're going to try to do. What maximum pressure does the dam have to withstand, right? So the maximum pressure is going to happen at the bottom, right? So all the way at the bottom. Now, what do we know? So if a dam is 45 meters deep, right? So it goes all the way down. So this is 45 meters. And it's 50 meters across. Okay, so this is 50 meters across there. So 50 meters, okay, across. Okay, so that's what we have in here. Now, all we really need to know is, okay, so with regards to the pressure, so we don't really care so much about, how long it is now, of course, because it's a dam. Okay, the width of the dam has to, withstand all the liquid, okay, or the water, otherwise it's going to flow around it. So that is fine for, thinking about this in terms of the dam blocking this particular water. But in terms of pressure, this is all just, okay, pressure in a fluid with regards to the depth, okay, that it is. So the maximum pressure is going to occur. So this is for part A. That maximum pressure is going to occur all the way at the bottom. So this is going to be the density times the gravity times the height, or the depth, okay, that you have. Now, if you're 45 meters deep, that's going to be the largest or maximum pressure that the dam is going to have to withstand. All the way at the top, it doesn't have to withstand any pressure at all, right? So at least not any gauge pressure. Sure, there might be some atmospheric pressure coming in, but no gauge pressure. So here we're just referring to gauge pressures. So meaning just what is coming from the water itself, okay? We're kind of ignoring the atmosphere above it. Okay, so now for this, water, so that is the density of water is 1,000 kilograms per meter cubed. Okay, so again, so it's something that you should be aware of. Now, the gravity you can assume, so 9.8 or 9.81, whatever it is that you might want to use. And now the height or the depth is 45. So in this case, we have 1,000 multiplied by 9.8 and multiplied by 45. That's going to be 441. It's already to 3 sig figs, and that's going to be pascals. So it's 441,000, okay, that we have in terms of the pressure. All right, so that's the first one. Now, what would the average pressure be? So this is a good question, because the average pressure, so as you're going through, what is interesting is that the pressure changes. Now it changes actually kind of linearly, okay, as you're going through, so it's proportionally to really the height in here, right? Notice that the density of water pretty much stays the same, okay, all the way through, and the gravity definitely doesn't change. So in this example, what you have is that pressure P is equal to, so if I go through this and I substitute these two in here, so what you're going to get is you're going to get 9,800 times the height. And this is, a linear relationship, okay, in here, because this doesn't really change. So if you were going to graph this, now if you think way back to math, if this is your y, this is your slope, this is your x, okay, the intercept is basically 0, right? So this is what your slope is. So if you're graphing this through, so you have this nice linear relationship, okay, for pressure. So as you're going through this, so let's put this as the height. So as the height continues between 0 and 45, right? So your pressure P is going to basically do this, right? And this is the maximum point, which we just found. So that's 441,000. And then this is 0 right at the top. So the average is basically halfway through. So we can easily find what the average is in here for this. So you can take the 2 points and basically divide by 2. Okay, so it's going to be half. Okay, so the pressure average is equal to, so that's the half point, which is 441,000, really divided by 2. So it's halfway down. Now we could have found that out by just simply substituting the height, h, which is 45, divided by 2. And we would get exactly the same thing. So we can take this answer, we can divide it by 2, and there you go. So it's going to be 220,500. You want to round to 3 significant figures, so 221, 0, I guess 00. That's going to be pascals. But let's keep that on the calculator. Maybe we need it for the next one. So that would have been the average pressure, right, on the dam. And that's why, as I said, on top, the dams are typically very narrow, and then they just kind of widen out, okay? So it kind of looks like this. The dam looks kind of like this on top, and then at the bottom, it's much wider because it has to support way more kind of force pushing against it over here and pressure, okay, that's going against this. All right, so let me just kind of squeeze out in here. Okay, so that was part B. Part C, what average force would the dam have to withstand? Okay, so that's a good question to ask. So the average, so this was for part B, right there. So what's part C? So now we need to know what the average force is. Well, this is the average pressure right here that we have. Now, the average force, well, this we can get from the equation. So pressure, or average pressure, is equal to the average force divided by the surface area. So now we do need the surface area in here of the dam. So now the surface area, so this is all of this, right? Now this is very easy because it's rectangular. So it's 45 times 50. So that's the surface area, and we're going to get exactly what this average is. So this right here is going to be nothing else but the average pressure multiplied by the area, which is 45 times 50. All right, so let's try it. So 220,500 multiplied by 45 times 50. Let me punch that in here. So that's my average pressure times, and then 45 times 50, and there you have it. So that's 6,125. Notice that it's enormous. This is newtons. All right. So that's quite a lot, right? Okay, in terms of the average. Okay, so that would have been the actual full force that you have on that entire entire thing. Okay, that you're going through. Right, so basically nothing on top, quite a lot at the bottom. But if we want the average, so if we know what the average pressure is, then we can find the average force. So it's pretty large, okay, but except it's spread out, okay, over the entire surface. And if you're rounding it to 3 significant figures, so it would have been 4, 9, 6, okay, and then a bunch of zeros. So this is 496, and then 0, 0, 0, 0, 0, 0 newtons. All right, so that's another example out of the way. All right, so here is question number 4. It's going to be the last one for this video, and I'll do the other half in another video, okay? And then I'll link them together. So I'll put up a link up above there once that second part is up. All right, so that's what you will see it. But let's finish this one and see how we can solve it. So a patient is receiving an injection via a 20 gauge needle. The needle has an outer diameter of 0.911 millimeters. So obviously the needles are, super thin, and an inner diameter of 0.609. Okay, so if you would take a cross section of this needle, so this is, so the needle's obviously kind of looks like this, except it's super thin, and we're kind of narrowing down, okay, on this tip, okay, in here. So the tip, so if you would look kind of, right at the tip there, so this is what it says, okay, so it has an outer, and then it also has an inner. Now, of course, it has to have that because, whatever we have inside has to flow through here. Okay, so this is basically whatever the needle is made out of. And then it has, okay, liquids, okay, of some kind, or, some kind of medication or maybe vaccine or something else that's passing through. They are telling us that the outer edge, so this is going to be, okay, so from this point to this point, so that's the outer edge right there. Let me do it on the side just so that it doesn't block it. Okay, so from there to there, that is equal to, so that outer is 0.911 millimeters. Now this is, notice the diameter, so it's not the radius. Now the inner one, so that inner one is from here to here, so that's the inner diameter. And that inner diameter, okay, that we have, so that's the smaller one, okay, that we have, that's 0.609 millimeters. 6, question 7, and question 8. So we'll see you back for those, okay? Take care. Thanks for watching. Bye, everybody.